Okay, Assalamualaikum wabarakatuh and good morning to everyone. So today we're going to start our operating system subjects lecture number 4, titled Processor Management. This is the e-learning mode for today's class 9 to 11. So definition terms: process, jobs or process or task. It is an activity entity that requires a set of resources, including a processor and special registers, to perform its functions. It also called a task. So process is like execution of the programs. So you have a Microsoft Word program, so you want to, or any other web server program, you want to execute a software on it. This is called a process. And a thread. Thread is a portion of process that can run independently. So thread is a unit of process. One process can have many threads or only one thread. Processors. So processors, also known as the CPU, is a part of the machine that performs the calculations and execute the programs. So you have here this is a process. So this is the process 1 and this is the thread 1, thread 2, thread 3 and so on. So process is a one big process and thread is the unit of process. So processor is also known as a CPU. So this we know what is a processor is. It performs the calculations and execute the programs. So in a way for you to understand better what is a process, so we have the analogy here. So here you buy a book. You buy a bookshelf and want to put it together to yourself. So you went to, I don't know, IKEA and you buy a nice bookshelf. But this is all in parts. You know, you have to assemble it one by one. Once you get home, you take out the instruction manual and start to read the instruction how to assemble the bookshelf. So the bookshelf is like part by parts. They have screws and everything. So the first step in the instruction is to join part A to part B with a 5 cm screw, and you achieve it successfully. So this is the process number 1, then the process being done. So you move on to step 2. Okay, and you are about to execute step 3. So step 2 you're already done. So you hear your little brother crying. Oh, there's some interruption. You quickly mark step 3 to indicate where you stop and go to check on your brother. So you mark step 3. You take a marker and stuff, and then you mark. You are on the step 3, but you have to do another jobs or task. So you find that your brother fell down and injured his knee. So you take out the first aid kit and start to bandage your brother's knee. So for the first aid kit and start to bandage your brother's knee is like a process number 1 for whole different jobs. So once your brother has been taken care of, you go back to assembling your bookshelf. So you continue once you have done with your brother, because this is the more priority, more concern that you have to concentrate on that job. So after you finish that, then you go back to assembling the bookshelf. So this is what you can compare to the OS. You're acting as the processor. So you have here a CPU. So you have here a CPU. It's a processor. And you are acting as the processor. There are two programs: assembling a bookshelf, job A, and bandaging your brother's injury, job B. So you have two jobs here. Job 1, and you have job 2. When you are following the instructions to assemble the bookshelf, each step performed is a process. So in job itself, you have this job 1 is bookshelf, assembly, and job 2 is what we call that, your brother, injury. Okay, so you have when you follow the instructions and the bookshelf, each step performed is a process. So in the job you have process 1, then you have process 2, and until so PN. And of course job 2 also you have process 1, process 2, and so on until process N. When you are following the instruction to assemble the bookshelf, each step is a process. Your brother's cry was interrupted. So let's say you're doing job 2 now. Let's say you are doing a job 3, process 3. You are doing now process 3, but there's some interruption from job 2. So there's an interruption, and then you go to the process number 1 for job 2, meaning that managing your brother, bandage, put some ointment or put some cream to that injury or so on. So your brother cry was an interrupt. Job 2 interrupt whatever current process you are in, and then you go to the process number 1 of job 2, because job 2 priority is much more have much more priority, and you have to concentrate on that, much more important. So when you left your bookshelf to treat brother, you left for higher priority program. So in terms of priority of job number 2 is higher than job number 1. So that's why you go for job 2 first. Even though you are in the current job 1, but when job 2 interrupt, you have to go to the job 2 process number 1. So priority, in terms of priority, job 2 is much more priority than job 1. And when you interrupted, you perform a context switch by marking step 3 on the instruction. So what you do here is you mark step 3. This is the, what we call that, a context switch. I just put here CW on job 3. You mark, okay, I'm in process 3, but somehow job 2 interrupt me, so I will go to job 2 first, complete that, and I will go back to the process 3. And this is what we call context switch, CS, context switch. When you are treating your brother, each step you execute is a process. So this is a process, this also is a process. Job 1, job 2, they have process. Job 1 have processes you have to follow in order, and job 2 also you have processes that you have to follow in order. When the job is complete, it is finished or terminated. So when you finish with job 2, finish, you will go back to job 1, process number 3, and you will continue until process N, until your job is finished. When a job is completed, it's finished or terminated. So you can free the, if this is a memory, RAM. So remember we learned last week, so you will free that memory. This slot will be free. In a multi-programming environment where there are many users and many jobs on the system, the processor must be allocated to each job fairly and efficiently. So a CPU, CPU module management must be able to allocate each job fairly and efficiently. Multi-programming requires that the processor be allocated to each job process for a period of time and deallocated when the period expires. So this is how the processor manage. So you have a time window, you have to complete this job and process, and then you deallocate the memory allocation or deallocate the CPU time for the job and go for a new one. If a program is deallocated during execution, it must be done in such a way that it can be restarted later as early as possible. So one processor can be shared by several jobs processors if and only if the OS has a scheduling policy. So you schedule your process, okay, process 1, what time, process 2, and so on. And scheduling algorithm to determine when to stop working on one job and proceed to another. In the analogy, you work on job A until a higher priority job B came along. So back to the bookshelf. First, you do a job 1, bookshelf assembly, process 1 done, process 2 done, process 3, and then you have interrupt from job 2. So you go to job 2, process number 1, and then you go until you finish, and then you go back. Before you go to job 2, you will do a context switch, mark, okay, I'm in process 3 when I left job 1. So when you're done with job 2, you will go to process 3, job number 1, and then you completed it. Okay, so the processor manager is composed of two subs managers. So you have composed of two sub-managers. So you have a job scheduler in charge of job scheduling and process scheduler in charge of process scheduling. So what we have here, okay, you have a job 1, J1, and then you have here J2 until job N. So this you have a job scheduling, and then you have a process 1, you have a process 2 until process N. This is same process 1, then you have process 2 and same until process N, and then you have process 1 here, process 2 until here, process N. So all this process, you have a process scheduler. So job you have a job, for job you have a job scheduler, and for process you have a process scheduler. So this is job. Maybe job 2 or job 3 is higher priority than job 1, so on. So but for general, you will start with job 1 until there is some call from higher priority job. You will be interrupt, but before you move to another job, you have to do a context switch on which process you are carrying on before you switch job. So that is a process that we learned in the previous slide. So the scheduling of the two jobs, assemble a bookshelf and bandage an injury, was on a first come first serve basis. First come and first serve basis. So first come first serve basis, just like first in first out. So each job is initiated by the job scheduler based on certain criteria. So the job scheduler will initiate all the jobs based on certain criteria, and job scheduler will manage which job has more priority than the others. Once a job is selected for execution, the job scheduler determines when each step or set of steps is executed. It is also based on a certain criteria. Okay, back to the bookshelf. Each step in the assembly, when you're assembling the bookshelf, each step in the assembly instruction is selected for execution by the process scheduler. So when you start job number 1 is bookshelf assembly. So when you start assembling the bookshelf, each step in the assembly instruction is selected for execution by the process scheduler. So the process scheduler will process or will manage all the process. You're done with process 1, process 2, and so on. Each job passes through a hierarchy of managers. First, it encounters the job scheduler, high level scheduler. So you have, okay, this is, if you follow the hierarchy, the highest one is job scheduler. Second is the process scheduler. The job scheduler is only concerned with selecting jobs from a queue of incoming jobs and placing them in a process queue. So the goal is put jobs in sequence that will use all the system resources as fully as possible. So you have a system queue, and then you have job 1, and then you have job 2 according to the queue, and job 3, and so on until job ends. So this is the queue process, jobs queue. So the jobs is only concerned with selecting jobs from a queue of incoming jobs and placing them in a process queue. Goal, put jobs in sequence that will use all of the system resources as fully as possible. So let's say you have so you select a job 1. This is a jobs queue, and then jobs 1. So jobs 1 have a process 1, process 2, process 3, and so on until process n. So this is the process queue, process queue. So put jobs in sequence that we use all system resources as fully as possible. So you have a jobs, okay, this is jobs 1, and then job have process, number of process. So you put it in a process queue. So the process scheduler takes over after the process scheduler takes over after job has been placed in a ready queue by the job scheduler. So okay, you have this is job 1. Job 1 is the status is ready. Maybe job 2 status wait, say wait. So if job is ready, so the job will go to the process queue according to the process of that jobs belonging to that jobs. It is the low level scheduler that assigns the CPU to execute the jobs placed in the queue. Determines which jobs gets the CPU when and how and for how long. So what is the other responsibility of job scheduler? Process scheduler decides when a job should be interrupted, determines which queue job. So remember the interrupted when your brother, back to the book self-assembly, when you're doing the book self-assembly, you heard that your brother fall down and injured himself, and you have to manage him first before you continue with the book chef assembly. So it also determines which queue a job should be moved during its execution. So queue job should be moved to do during its execution. This is one of the process scheduler's tasks. Determines a job has concluded and should be terminated. So when the job has been done, you have to deallocate in the CPU and the memory. To schedule the CPU, the process scheduler takes advantage of a common trait among most programs. They alternate between CPU and input cycles. So process scheduler take advantage of the common trait most programs, alternating between the CPU and output cycles. So you have here, and then you have here a CPU, and CPU is alternating with the input output cycles. So this is one of the process schedulers. So you have an input output cycle, you print F, enter A, and then it will display A, and then you you try to enter B, and then it will display a B value. So this is CPU cycle. C execution, C is equal to A and B, and so on, and it alternate back to the input output cycle. This is the initial input output cycle. Then you have a CPU cycle doing all the logic arithmetic here, and then you have an input output cycle, and then it will execute all this from the CPU cycle. The program has one relatively long CPU cycle and two brief input output cycle. So the duration and frequency of CPU cycles vary from program to program, but they are general tendencies that can be exploited when selecting a scheduling algorithm. So you have one to schedule algorithm. Duration and frequency of CPU cycle vary from program to program, but they are general tendencies can be exploited. The first one is input-output bound jobs. Example, printing a series of documents have many brief CPU cycles and long input-output cycle. And then you have a CPU bound jobs, finding the first 300 prime numbers, have long CPU cycles and shorter input-output cycle. So this some example of the process scheduler. So in a highly interactive environment, there is a third layer of process manager called the middle level scheduler. When the system is overloaded, almost full its scope capacity or over its scope capacity, the middle level scheduler removes active jobs from memory to reduce the degree of multi-programming and allows jobs to be completed faster. So when there is a overloaded over jobs, middle level scheduler will remove any active job from memory to reduce the degree of multi-programming and allow jobs to be completed faster. So it handles swapping out jobs and later swapping that back in. So when you not print it, when your job is execute and suddenly there is some interruption or it's overloaded, the job will be removed in the main memory and put in somewhere else. And then after that particular other jobs are done, you put back and swap back in the memory. So a job is in one of 5 states: hold to ready, hold to ready, to running, to waiting, and finally finish. So remember, if a ready wait it's actually not waiting hold, but it's the same one. Running to waiting and finally finish. So this is the you have a waiting as well. And finally, so this is the job and process status. So you have here, you have a whole job scheduler balancing use of resource, memory, and device. This is what is a job scheduler task. Then you have a process scheduler algorithm, and then you have a job scheduler. When finished, it release the resources. So you have whole, ready, running, finish, or waiting. So when it's ready, it can be run, and then after that, it can be completed. So process scheduler, when they have a signal from device manager or page interrupt handler, the jobs, any jobs will be wait in the queue. So because the CPU has to execute much more priority jobs, so the current job will be in waiting and execute new jobs. And after waiting is finished, it's ready to be run, and then it's run and then it finish. So this is a process scheduler input output request or page fault. Remember page fault, whenever you want to allocate a new job or new value, you have to you will be in the situation of page fault. Remember last week lecture, the goal is to reduce the page fault. So again, a user submit job to a system via batch or interactive job, and when the job is accepted, is accepted by the system, it is put on hold. Okay, job is coming, and then when the job is accepted, it will put on hold. And then job spooler creates a table that contains the characteristic of each job in the queue, estimated of the CPU time, priority, special input required, and maximum memory required. So this is what the process will done. So you have a hold to ready. Job scheduler checks availability of main memory and any request devices. Ready to running. Process scheduler according to predefined algorithm like first come first serve. And running to ready. Process scheduler according to the predefined time limit or criterion or policy interrupt. So ready to running is when you're ready to running, you put after the hold, you ready, and then you run, execute a program. Running to ready, when you execute a job and then there are some interruption, though you will put to the ready waiting and then ready back. So running to waiting, process scheduler initiated by an instruction in the job such as read, write, or other input output requests. or waiting to ready. Process scheduler initiate by the signal from the input-output device manager that input-output request has been satisfied. Or running to finish. Jobs done, completed, deallocate the memory and the CPU. So, process control block. When you have a process control block, you have information about the jobs, what it is, where it's going, how much processing has been completed, and where it's stored, and how much is spent in using resources. So this is the contents of process control block. The first one is a process identification. Each job is identified by user identification and pointer connecting to its descriptor. And then you have a process status, either whole, ready, waiting, running, so on. And then you have a process state, process status word, the current instruction counter and register content when the job isn't running. And then you have a register contents, the comments of the register if the job has been interrupted and is waiting to resume processing. Main memory, important such as address, and then resources, info about resources allocated to this job. Each resources has an ID field listing its type and field describing details of its allocations, such as the sector address on disk. And then you have a process priority used by the priority scheduling algorithm to select which job will run next. And then also you have accounting, content information for billing and performance measurement. Indicates what resource the job used and how long. So this is all the timing and stuff for the accounting. So a job's PCB, okay, in a nutshell, so jobs include all this process identification, status, and process state, and also the accounting, how long the job, when the job is done, and keep all the record. So this is what the accounting means. So a process scheduler, a job's process control block is created when the job scheduler accepts the job and is updated as the job progresses from beginning to termination. The process control block contains all info required by the OS to manage the processing of the job. The progress of job execution is noted in PCB. So the PCB are linked to form a query. This is from user, and then a job is accepted, it is put on hold, and then job scheduler will change it to the ready, and then ready, it will start to run. If anything happens like interruption or more higher priority jobs is coming, go back to the ready, or it will run and finish. I mean, in the running process, you have the this input output queue, tape input output queue, printer, and so on. This is input output request or input output devices. So this is when you run, you put all this in the queue, then you're waiting, then you're ready, and you run again. So the queues are managed in orderly manner that is determined by the process scheduling policies and algorithm. So in a multi-programming environment, there are usually more jobs that can be run at one time. So multi-programming environment, last time it was in a serial mode, one jobs at one time. So this, you have multi-programming environment, you can actually code so that you can run the jobs more than one jobs at one time. So in order to schedule jobs, the OS need to resolve three limitations. The first one is there are finite numbers of resources, disk drive, printers, and so on. Certain resources once allocated cannot be shared. It's like printer. When you're doing a printer, you cannot share with others. Certain resources require operator intervention, like a tape drive, but this is the old techniques. So what is a good process scheduling policy? The first one is to maximize throughput, run as many jobs as possible in a given amount of time. So can be accomplished easily by running only short jobs jobs or running jobs without interruptions. The second one is minimize response times. Quickly turn around interactive requests accomplished by running only interactive jobs and let batch jobs wait until the interactive load cease. Minimize turnaround time. Move entire jobs in and out of the system quickly. Could be done by running all batch jobs first because batch jobs can be grouped to run more efficiently than interactive jobs. Minimize waiting time. Move jobs out of the ready queue as quickly as possible. Maximize CPU efficiency. Keep the CPU busy 100% of the time done by running only CPU bound jobs, and ensure fairness to all jobs. Give everyone an equal amount of CPU and input output time. So one criteria may contradict another. How do we choose a good scheduling policy? So this is up to you. This is up to the OS. A system designer must consider or determine which criteria are most important. So this mostly up to the OS designer. Example, the objective is to maximize CPU utilization while minimizing response time and balancing the use of all system components through a mix of input-output bound and CPU bound jobs. So the process scheduler relies on a process scheduling algorithm to allocate the CPU and move jobs through the systems. So this is algorithm. How do you allocate the jobs in the CPU and move along jobs throughout the system? So you have a 6 process scheduling algorithm. First come, first serve, shortest jobs next, priority scheduling, shortest remaining time, round robin, and multi-level queues. So the first come, first serve is a non-preemptive. Non-preemptive meaning that handles jobs according to the arrival time. It will not hold the job. Once it's coming, it will it will run the jobs. Very simple, implemented using first in, first out queue. It is actually good for last time a batch system, but not acceptable in a modern computing. When the job enters the system, its PCB is lined to the end of the ready queue and is removed when the processor becomes available. So here you have a job A coming in first. You take 15. Let's say this is a 15-second. Job B you take until 17 seconds. Another 2, and job C is 18. So if A and B arrive almost simultaneously, the turnaround time for job A is 15 because we have to done job A first. And then according to the, in order, job A 15, job B takes 2 seconds, 15 from 17, and job C takes 1 second, 17 to 18. But the average turnaround time is 15 plus 17 plus 18 is 16.67. Jobs A and B have a CPU cycle of 15 millisecond, 2 millisecond, and 1 millisecond respectively. So this is the average turnaround time. So if the jobs arrive in different order, say CBA, the turnaround time for job A is 18, job B is 3, and job C is 1. So the average turnaround time is 18 plus 3 plus 1, 7.3. So this is much more like arrive in a different order. If let's say the C arrive first, and then B arrive after that, and job A arrive after that. So the turnaround time will be different, much more lower. So the disadvantage of first come first serve, the average turnaround time vary widely and are seldom minimized. So you have 2 conditions here. If A and B arrive almost simultaneously, so you put priority job A, job B, and job C, and turnaround time is 16.167. And if jobs in different order, let's say C, B, and A, so you have a lower turnaround time. So next we're going to go for shortest jobs next. It's a non-preemptive scheduling algorithm again. Whichever coming first will be execute, but they have a more complex algorithm than the first FCFS, first come first serve. Also known as the shortest job first. Handles jobs based on the length of their CPU cycle time. Easiest to implement in batch environments where the estimated CPU time required is stated by the user at the start of a job. So you have here job A. Okay, job A arrive first. Job A, job B, C, and D. Let's say this one arrive almost at the same time, so shortest job first will be B, and then after B is D, after D is A, and last one is C. So you have a 2 plus 6 plus 11 plus 17 divided by 4, so you have a average turnaround time is 9. So the average is actually calculated by this one, and you can use the formula T1 times N, T2 plus T2 times N minus 1 plus T3 times N minus 2, and so on. So if you have here N is a 4 here, and then N in this example N is 4 and T1 is 4 N is a 4. Yes, and then you have here T1, T2, and so on. So this is a formula for shortest jobs next. SDN is optimal only when all jobs are available at the same time and CPU estimates are available and accurate. Meaning that, let's say you have a job A, B, C, D. Let's say job A arrive first. Job A, it will do the job A first until it finish. So it depends on the which job arrive first as well. But if the job arrives almost in the same time, so it will choose the shortest, the shortest one first. So it's only optimal when all jobs are available at the same time and CPU estimates are available and accurate. Okay, we move to the priority scheduling. It's a non-preemptive algorithm. Again, one of the most common algorithms for batch systems. Not really useful for the multi-programming. It gives preferential treatment to important jobs, allow programs with the highest priority to be processed first, and they are not interrupted until their CPU cycles are completed or a natural wait occurs. So priorities are assigned by a system administrator using characteristics extrinsic to the jobs. For example, assigned based on the position of users. Lecturers first, then research assistant, then students. So this is a position. Lecturer have a higher position grade. Then RA also, and the last one is the students. So in a commercial environment, users can purchase higher priority to guarantee their jobs are processed the fastest. So priorities can also be determined by the process manager based on intrinsic characteristics such as memory requirements, where jobs requiring large amounts of memory could be allocated lower priorities, or conversely, number and type of peripheral devices. Jobs requiring many peripheral devices are allocated lower priorities, those requesting fewer devices than those requesting fewer devices. Total CPU time. Job with long estimated runtime are assigned lower priorities, and amount of time already spent in the system based on the total amount of elapsed time since the job was accepted for processing. Some systems increase the priority of jobs that have been in the system for unusually long time to expedite their exit, or known as aging. So when the jobs have been there for a while, and then it's not completed yet, and then the system, the priority scheduling will give this a higher priority, so that in a hope that it will finish faster, and to increase their exit time. This is also known as aging. And then we have a shortest remaining time. It's a preemptive version. This is a preemptive version of SJN. The process is allocated to the job closest to completion. An executing job can be preempted if a newer job in the ready queue has a shorter completion time. Cannot be implemented in an interactive system because it requires advanced knowledge of CPU time required. So it also incurs more overhead than shortest job SDN because the OS has to monitor the CPU time for all jobs in the ready queue and must perform context switching for jobs being swapped at preemption time. So let's say you have here arrival time A, B, C, and D, and you have a turnaround here. So average turnaround you add, and then you have 6.25. So let's say here job A is preempted by job B because job B. This actually it requires Quite advanced knowledge of CPU time required. So this is much more complex to implement. This is quite the best one, but quite complex because CPU must have a knowledge. Okay, when the job's coming in, CPU must know how many times or how long this job can be executed in advance. So let's say you have a job A printed by job. Okay, job A come first. After 1 second, let's say job B has been because job B because job B has less CPU time remaining, and then so on. After that, I mean they complete job B and then job C coming in. Job C has lower time first, so it will be execute first and then go back to job B. And then when job B done, job D has the lowest lowest CPU time, so job D will be done first, and we'll go back to job A to finish the remaining. Compare the same job problem using SJN policy. Let's say job A come first, 6, and then all other jobs are in the queue. So when A come first, you have to complete A for SJN, shortest job, and then you have B, C, and D. So you take B. B, C, and D. C has the lowest, shortest job time. So C is priority first. Between B and D, B has lower priority time, so B will be executed, and then D. So you must remember this job A come first, regardless what's the turnaround time. The system will execute job A first, and then we'll go and check for job C, B, and D. So shortest remaining time is faster than SJN, neglecting context switching that is required for preemptive algorithms. So when job A is preempted, all of its processing info must be saved in its PCB for later when execution is continued. The content of job B's PCB are loaded into the register so it can start running again. Context switching still takes CPU time and may diminish the advantage of SRT. So context switching is still there, and it will defeat the purpose of the SRT. Then you go to the round robin. It's a preemptive process scheduling algorithm that is used extensively in interactive system. It's not based on job characteristic. A predetermined slice of time is given to each job. So you have a round robin here. When you have a round robin, so you go round. So this job 1. Job 1, let's say given like 5 seconds. 5 seconds. After 5 seconds, regardless whether it's finished or not, it will go to job 2. Job 2, let's say give 3 seconds. Regardless whether it finish up, we will go to job 3 and so on. Job 4 and so on until all the jobs are finished. This is what is round robin. It's not based on job characteristic. A predetermined slice of time is given to each job to ensure that CPU is shared among all active processes and monopolize the CPU. A time slice is called a time quantum that varies between 100 milliseconds to 1 or 2 seconds. Jobs are placed in a ready queue using a first come, first serve scheme. So the process scheduler selects the first job from the front of the queue, set a timer to the time quantum, and allocate the CPU to this job. The job has not finished executing. So let's say job 1 actually take 10 seconds. After 5 seconds, job 1 will be whole, and then you start job 2. Job 2, 3 seconds. Maybe it takes about 5 seconds. Not finished yet, move to job 3 and job 4, and then go back to job 1. Job 1 finish after 5 because 5 seconds already done. Then another 5 seconds, and job 1 needs another 5 seconds. Job 1 first, job 2 also need another 2 seconds, and so on. So it is not prioritizing or anything the previous algorithm does. It only allocate a job time in the round robin. The round robin only allocated a job time for each job, and if the job is not yet completed, it will go back to the next. It will go to the next job while putting the previous job in hold. So if the job CPU cycles is shorter than the time quantum, either if this job last CPU cycle is finished, all resources are released and the complete job is returned to the user, or if the CPU cycle has been interrupted by an input request, the info about the job is saved in its PCB and is linked at the end of the appropriate input output queue. Later it is returned to the ready queue. So in the round robin, you have job A, job B, job C. Job A, 4, job B, and then after 4 seconds, not finished, job B, done. Job B only take 4, so job B done. And then job C, job C actually take 9 seconds, but it only for the first allocation only allocate 4 seconds, so job C on hold, go to job D, and so on. So the average turnaround time is quite high, 18.25. Its efficiency depends on the size of the time quantum in relation to the average CPU time. If the quantum is too large, it becomes the first come first serve scheme. If it's too small, the amount of context switching slows down the job execution and increases the overhead dramatically. So you have a time quantum here. So there's no context switching, therefore it's no overhead. The CPU cycle ends shortly before the time quantum expires. No difference between round robin and FCFS algorithm. This one for the A. And then you go for B. Time quantum for B. So one context switch. The job is preempted once when the time quantum expires. So there's some overhead for context switching. There is also a delayed turnaround based on the number of jobs in the system. So for C, time quantum 1, so there are a lot of context switch, so this increase the overhead. So in round robin, in order to implement it, you must know the best quantum size. So it depends on the system. This is the system designer must know what is the best quantum size. And some some guidelines, rule of thumb, it should be long enough to allow 80% of the CPU cycles to run the completion. It should be at least 100 times longer than the time required to perform one context switch. So we go to the multiple level queues. It's not a separate scheduling algorithm. It works in conjunction with other schemes. Example of multi-level queues, a priority-based system with different queues for each priority level, and a system with one queue of CPU-bound jobs and another for input-output bound jobs. The process scheduler alternate between the two queues. So for example, in environment that supports batch and interactive jobs, like the modern computer, the batch jobs are put in one queue called the background queue, while the interactive jobs are put on the foreground queue and given priority over the background queue. So the batch jobs are put in the one queue called the background queue, while the jobs are put on the foreground queue and given priority over the background queue. So foreground has a higher priority than the background queue, because foreground is in the front and then it has higher priority, so we'll execute first and given the higher priority than the background queue. So what is the issues of multiple level queues? Is the processor allocated to jobs in the first queue until it's empty before moving to the next queue, or does it travel from queue to queue? Is this fair to those who have earned or paid for a higher priority? Who knows? Is it fair to a low priority queue? Again, and can jobs in low priority queue move up to a higher priority queue? So this is the system designer must consider all this when it designs the scheduler. So case 1, no movement between queues. It's very simple policy, not complex. The CPU is allocated to jobs in the high priority queue using FCFS, and it allocated to jobs in low priority queues only when high priority queues are empty. So it will execute the higher priority one, then to the lower priority. Okay, for movement between queues, the policy adjusts the priorities assigned to each job. High priority jobs are treated like all other ones they are in the system. When the time quantum expires, the job is preempted and moved to the end of the next lower queue. A job's priorities may also be increased when it issues an import request before its time quantum expires. And for case 3, variable time quantum per queue is variation of the movement between queues policy. Allow for faster turnaround of CPU bound jobs. And each queue is given a time quantum twice as long as the previous queue. The highest queue may have a time quantum of 100 milliseconds. The second highest queue has a time quantum of 200 milliseconds, and so on. So it's actually a variation of movement between queues policy. Allow faster turnaround, and each queue is given a time quantum twice as long as the previous one. So if the first one have 100 milliseconds, the second one is given 200 milliseconds, and so on. If a job does not finish its CPU cycle in the first quantum, it moves to the end of the next lower level queue, and when the process is allocated to it, it executes twice as long as before. So let's say you have a job cycle, you have a quantum of 10 seconds, and when the time quantums expire, you haven't finished the job. So you move to the next lower level queue. When you come back to the job, and when the job's coming back to the, let's say, job A, it will execute twice as long as before. So it has a time quantum of 20 seconds. And case 4, aging. Aging, when you have this job already been there for quite a while and the processor cannot wait to remove it. I mean, the processor or the scheduler cannot wait to remove this job, so given a high priority. Ensure that jobs in the lower level queue will eventually complete their execution. So the OS keeps track of each job's waiting time, and when a job gets too old, reaches a certain time limit, it is moved to the next highest queue, and so on until it reaches the top queue. So you already been here for so long, so I will give you high priority so that you can deallocate faster, or you can be removed. Your task can be removed in a faster way, or to expedite your removal. Guards against indefinite postponement that leads to starvation. So the job is already too long in the queue, so you have to go to the indefinite postponement. So that's it for today. Thank you very much.